Hello, this is Mr. Klingler, and I'm here to explain how to solve systems, otherwise known as how to solve the forces acting between two or more objects. Alright, so imagine we have an Atwood machine. An Atwood machine is a pulley with a block hanging over each end. And I'd like to know how this system is going to behave. Well, the first question I can ask is, what direction is this thing going to move? Well, assuming the pulley is stationary, it should make sense to us that the heavier block is going to move down and the other block will move up. Alright, which one of these blocks do you think will have the greater acceleration? Well, it should make sense that they're connected by a string. And therefore, the acceleration for each block should be the same. Which one of these two has a greater tension in the string acting upon it? That's actually a fairly subtle question and has to do with Newton's third law. Let's draw a free body diagram for each block. Well, for this block, we have the force of weight pulling down, and we have a force of tension pulling up. For this block, a force of weight and a force of tension. But realize, these forces of tension are the same by Newton's third law. The force of the 3 kilogram block pulling on the 2 kilogram block is the same as the force of the 2 kilogram block pulling on the 3 kilogram block. As long as the string is massless, the tension will be the same everywhere along the string. Another question we could ask, what do we think the acceleration of the system will be? This block is going to fall, this one's going to rise. What is the acceleration? Is it going to be g, less than g, or more than g? It would be really odd if it were greater than g. Something strange would be happening. It shouldn't be less than g because in order for this block to fall with the acceleration of gravity, this force would have to disappear. Therefore, it makes sense that it should accelerate with something less than g. Alright, another question we could ask is, what is a possible range of tensions that might exist in the string? In a moment, we'll solve for that exactly, but for now, what is a possible range? Well, I need this block to go down. In order for this block to go down, the force of tension has to be less than about 30 newtons. This block needs to rise. In order for this block to rise, the force of tension has to be greater than 20 newtons. So offhand, we know, and I'll make note of it right here, that this has to be true. Okay. Now let's take a moment to actually ask a force-related question. Let's find the acceleration of the system. Well, in order to do that, we're going to need a strategy. Here are the problem-solving steps that I use when trying to solve a system. I call this method block by block because we're going to draw a free body diagram of each block. So let's try to follow it. Step 1. Draw a free body diagram for each object. Done. Pick a direction of motion. So how is this thing going to move? The problem is it doesn't just sort of move in one direction, not just the x or the y. This moves up and this moves down. So when I designate a direction of motion, I need to say what movement is positive. For me, I will call that motion positive, since I believe this block will fall and this block will rise. Write a sum of the forces equation for each object. Okay, for this object, it should make sense to you that I'm writing force of weight first and subtracting the force of tension because of how I've set my direction. Let me do this for the second object. Notice I have two equations and two unknowns. I can solve this. Keep in mind, these accelerations are the same, and I have an action-reaction pair in my equations. That's how these two objects are relating to one another. These force of tensions are the same. So now I can solve this. If I'm solving for the acceleration, I think the fastest method may be just to add them together. If I do that, I find the acceleration is 2 meters per second squared. All right, that's not so bad. Let me show you another method for solving these kinds of problems. I call this the systems method. Flatten, box. Okay, it's a little obscure, but I'll explain it to you right now. Imagine I want to find the acceleration. All right, I draw a free body diagram for each object. I pick a direction of motion. Now I need to flatten. If you look at this, you can imagine that it's really tug of war between this weight and that weight. In fact, I could take this and flatten it out such that the one weight was pulling this way and the other weight was pulling that way. What would it look like? Notice these forces of tensions are pointing opposite and equal to each other. Box. Well, if I think about it, what's really going on is I am simply having these two try to pull this blue box one way or the other. I can write a sum of the forces equation for all my non-action reaction pairs. These two cancel out, so I know they're not going to affect the acceleration. The only forces that affect the acceleration are this and this. Therefore, if I write a sum of the forces equation, And it's simply the force of weight 3 minus the force of weight 2. What do I write here? I know it's equal to ma, but what's my mass? My mass is the mass of the system, in this case 5. And once again, we end up with an acceleration of 2. I would note that the systems method is a little subtle. Sometimes it is not clear which forces you need to include in the systems equation and which forces you do not. Further, the systems method will not allow you to solve for an internal force. So if you want to find the force of tension in this problem, you have to do it block by block. The short version is, whenever you're in doubt, try solving block by block. As you get a hang of it, you can start using the systems method as a shortcut for solving your force problems.